Hello everyone, welcome to the mathematics in my channel. In this video we are going to evaluate these two integrals. First one, integral from 0 to infinity arctan square of x over x square, and second one, integral from 0 to infinity arctan of x square over x square dx. Okay, first let's solve the first integral. We can begin with integration by parts. So here integral from 0 to infinity. Now as a first function I am going to take arctan square of x, then we know d by dx, then integration of 1 over x square. We know integration of 1 over x square is equal to minus 1 over x dx. Then we know product of these two functions, so we have minus 1 over x times arctan square of x, limit from 0 to infinity, then minus, and here we have another minus sign, so minus minus will be plus, integral from 0 to infinity. Now rewrite first function, so we have 1 over x times, now derivative of first function, this function arctan square of x, we know 2 times arctan of x, then according to chain rule the derivative of arctan of x, we know 1 over 1 plus x square dx. Okay, then if we apply limit here, we know this part will be 0, and now we have to evaluate this integral. To evaluate this integral, we can take a substitution. So let's take x is equal to tan of theta, then differentiation dx is equal to secant square of theta d theta. Now we can plug in. So here first this 2 is a constant, so we can write outside the integral sign, then integral, and now we should change the boundary. Lower limit when x approaches to 0, we know theta also approaches to 0. In upper limit when x approaches to infinity, we know tan of pi over 2, so upper limit approaches to pi over 2. Then here we have arctan of x. Arctan of x, we know theta, then dx, we know secant square of theta d theta over x we have tan of theta times 1 plus x square, we know tan square of theta. Well, now we can simplify, because we know 1 plus tan square of theta is equal to secant square of theta. Therefore secant square of theta, 1 plus tan square of theta get cancelled. So we have 2 times integral from 0 to pi over 2. Here theta, 1 over tan of theta, we know cotangent of theta d theta. Well, to evaluate integral theta times cotangent of theta, we can again use integration by parts method, IBP. So 2 times integral from 0 to pi over 2. Now as a first function I am going to take theta, then d by d theta. Here integration of cotangent of theta, we know natural log of sine of theta d theta, then product of these two functions, so we have 2 times theta times natural log of sine of theta, limit from 0 to pi over 2, minus 2 times integral from 0 to pi over 2. Now rewrite this function, natural log of sine of theta times derivative of theta, we know 1, so here we have only d theta. Now again if we apply upper boundary and lower boundary, we know this part will be again 0, so we have minus 2 times this integral. This is a famous integral. In the previous videos we solved this integral. If you like to watch that video, I will add the link in the description and also make a card. So we know this integral is equal to minus pi over 2 times natural log of 2, then we know these 2 get cancelled, minus minus, we know plus, so we have pi times natural log of 2. Okay, this is the answer for first integral. Well, then we are going to evaluate our second integral. Integral from 0 to infinity arctan of x square over x square dx. Well, what do you think? How to evaluate? Okay, in this video, I'm going to use the Feynman technique. Therefore, I'm going to introduce the function f of a. F of a is equal to integral from 0 to infinity arctan of ax square over x square dx. Then if we plug in 1, we know f of 1 is equal to our integral I. Then we know we should differentiate with respect to a. So here f dash of a is equal to integral from 0 to infinity, here 1 over x square times derivative of arctan, we know 1 over 1 plus here a square x to the 4th power. Then according to chain rule, we should multiply by the coefficient of a, so x square, so here x square times dx. Then we know this x square get cancelled. So now we have integral from 0 to infinity 1 over 1 plus a square times x to the 4th. To evaluate this integral, let's take the substitution. Ax square is equal to tan of u. Then if we differentiate, 2 times a x dx is equal to secant square of u times du. Then we can isolate the dx. We know dx is equal to secant square of u times du over here 2 times a times x. X we know here we can isolate the x. X we know square root of tan of u, square root of tan of u over the square root of a. Then we can simplify. Here we know we have secant square of u times du over this square root of a get cancelled, and here we have the square root of a. So we have 2 times the square root of a times the square root of tan of u. Well, then we can plug in. So we have here, now we know limit we should change when x approaches to 0. We know u also approaches to 0. Upper limit when x approaches to infinity, we know tan of pi over 2. So upper limit pi over 2. Then in the numerator we have dx. Dx we know secant square of u times du over 2 times the square root of a times the square root of tan of u times, now here 1 plus a square x to the 4th power. So we have 1 plus here tan square of u. Okay, then we know 1 plus tan square of u is equal to secant square of u. So this secant square of u get cancelled. 2 times the square root of a is a constant. So 2 times the square root of a, integral from 0 to pi over 2. Now we have 1 over 1 over square root of tan of u du. Well, then we can convert tan function to sine and cosine. Therefore we have 1 over 2 times the square root of a, integral from 0 to pi over 2 sine raised to the 1 half, so minus 1 half times u cosine raised to the 1 half times u du. Well, then recall the beta function. We know beta of xy is equal to 2 times integral from 0 to pi over 2 sine raised to the 2x minus 1 of theta cosine raised to the 2y minus 1 of theta d theta. In the previous video, I derived this beta function formula If you like to watch, search the beta function. Okay, then let's move to our integral. Now we know here 1 over 2 times square root of a times, now this integral we know this is equal to 1/2 beta of, now we know 2x minus 1 is equal to minus 1/2. So if we isolate the x, we know 1 over 4. Then 2y minus 1 is equal to 1/2. Then if we isolate the y, we know we have 3 over 4. So we have here 3 over 4. Then we know the relation between gamma function and beta function. Beta of xy is equal to gamma of x times gamma of y over gamma of x plus y. Therefore we can write here 1 over 4 times the square root of a times gamma of 1 over 4 times gamma of 3 over 4 over gamma of 1 over 4 plus 3 over 4. Now we know this is equal to gamma of 1, and gamma of 1 we know 1. So here 1 over 4 times the square root of a times here gamma of 1 over 4. Gamma of 3 over 4 we can write gamma of 1 minus 1 over 4. Then I have to call the Euler's reflection formula. We know gamma of x times gamma of 1 minus x is equal to pi over sine of pi x. So here we have 1 over 4 times square root of a times pi over sine of pi times, now here instead of x we have 1 over 4, so sine of pi over 4. Now we know pi over 4 times square root of a times sine of pi over 4 we know 1 over square root of 2, so here we have the square root of 2. So if we simplify, we have pi over 2 times square root of 2 times square root of a. Now we know this is equal to f dash of a. Then if we integrate, we have f of a is equal to pi over 2 times square root of 2 times integration of 1 over square root of a. We know 2 times square root of a plus constant. Now here we know these two get cancelled. Now we know f of 0 is equal to here we have f of a, so f of 0 is equal to 0, so f of 0 is equal to 0, and we know this is equal to here also we know 0, so c is equal to 0, so f of a is equal to pi over the square root of 2 times the square root of a. Then we know our integral I is equal to here f of 1, so we can write now I is equal to f of 1, and this is equal to pi over the square root of 2. Okay, this is the answer for our second integral. Thank you for watching.